Hey y'all, my name's Tatum Rask. I'm a PhD student at Colorado State University, and this tutorial is going to be all about Möbius inversion and its uses in persistent homology. So we're going to jump straight into it. What is Möbius inversion? Well, let's just look at the setup that we're going to be studying today. So let's look at a locally finite poset. Maybe we have the poset P that I've drawn on the screen. Often when I draw posets in this tutorial, I'm going to be drawing the Hasse diagrams. What I mean by that is as you imagine going up in the screen, every time there is a line, imagine there is a inequality. So in this poset, we say that A is less than or equal to C, A is less than or equal to B is less than or equal to D. And although we don't show the lines that represent the transitive property, we're going to assume they hold. So A is less than or equal to D. And by locally finite poset, I just mean that between any two elements, there is a finite number of elements in the poset. And we're going to be studying functions on our poset. So as one example, I've drawn the function f. Again, this is going to be a function that assigns to every element in our poset a real number. And if we have a function on a poset, we can define its Möbius inverse. Now, there are some conditions we have to put on this function. Either the function has to have a bottom element, or there needs to be a element such that everything below it, that function will evaluate it to 0. But with those conditions, we can define its Möbius inverse. I'm going to call it delta f. And this Möbius inverse is going to be the unique function that satisfies this equality on the screen. Okay, so then here's an example. Let's look at that function f we saw earlier. Its Möbius inverse I have drawn in P. And let's just check that this equality does actually hold. Notice that our function f at our element A has to evaluate to 1, meaning that our Möbius function at A will also evaluate to 1. But f at B evaluates to 2. And so our Möbius function has to evaluate to 1, so that the sum of these highlighted or circled elements sum to 2. And then you can see the same thing. F at D evaluates to 3. So everything in our poset, when we evaluate our Möbius inverse, has to sum to 3. Okay. And often we call the Möbius inverse the combinatorial derivative. Again, if you go back to the screen, you can kind of see a sense that that Möbius inverse tracks changes in the function on our poset. But also, if you stare at this Möbius inverse function or formula, it looks kind of like the fundamental theorem of calculus. Here, the sum plays the role of the integral. Our function plays the role of, well, our function that we're taking the derivative of. And our Möbius inverse plays the role of our derivative. This motivates why we call our Möbius inverse the combinatorial derivative. Now, before we move on to where this comes up in persistence, I want to give a classical example of Möbius inversion. And as far as I know, this is where we get the name Möbius. And that comes from number theory. So suppose we have an integer n, and we look at its poset of divisors. Just as an example, I've shown the poset of divisors for our integer 6. And what Euler's totient function does is, given an integer, it counts the number of integers less than or equal to your chosen one that are relatively prime to your chosen one. So for n equals 6, Euler's totient function evaluated at 6 is 2, because our two integers that are relatively prime are 1 and 5. And it turns out that Euler's totient function is the classical example of Möbius inversion. We have the following formula for Euler's totient function. And notice that what I've highlighted in purple is going to give us the Möbius inverse of Euler's totient function. So we look at the sum over all integers that divide our number n. Then we take that divisor and multiply it by this new function evaluated at n divided by d, where d is the divisor. This new function is called the Möbius function. And I won't read off the formula to you, but you can see it on the board. And in fact, it's perhaps more instructive to look at an example. So again, let's go back to our integer 6. The Euler totient function at 6 evaluates to 2. So let's see what happens if we compute the Möbius inverse of Euler's totient function on this poset of divisors. So let's just look at one example here. Let's maybe look at our Möbius function, or the Möbius inverse of Euler's totient function, evaluated at 3. All right, so what we're going to do is we're going to look at the divisor. I said 3, but I highlighted 2 earlier. Let's actually look at 3. And we're going to multiply it by our Möbius function evaluated at 6 divided by 3, so 2. Notice that 2 is a product of just one distinct prime itself. So we're going to have 3 times minus 1. And so our Möbius inverse evaluated at the divisor 3 is going to be minus 3. And indeed, what you can see is that if we evaluate our Euler-Socian function at 6, we get 2. What that tells us is that if we sum up this Möbius inverse at everything 6 or below, we get 2. Indeed, 6 minus 2 minus 3 plus 1 gives us 2. So Euler-Socian function is the classical example of Möbius inversion. But if we go back to this idea of the Möbius inversion, giving us some notion of taking combinatorial derivatives, what does this have to do with applied topology? Why am I telling you all about it in this AAPRN tutorial-a-thon? Well, Möbius inversion, it turns out, is deeply related to persistent homology. All right, so y'all have probably seen a few talks from this tutorial-a-thon on persistent homology, but I want to give a very brief overview of the pipeline and then just highlight how Möbius inversion shows up. All right, so suppose we have some simplicial complex, so in this case, vertices and edges, that is growing as we increase some parameter values. So here we start with just 3 edges or 3 vertices, and then we slowly add edges. What we might want to do is we might want to track how the number of connected components change with time. So what we can do is we can compute something called the rank function, and the rank function will say, okay, what are the number of connected components that exist at my start interval that still exist right before my end interval? So for example, if we look at this interval 2, 3, we see that our rank function gives us a 2. If we look at step 2 of our filtration, there are 2 connected components, and both of them still exist right before 3. And then if we want to compute the persistence diagram, so that is we want to track precisely when these connected components appear in our persistence diagram and when they disappear, we are going to apply this inclusion-exclusion formula. So you can read the formula on the screen, but again, let's look at our interval 2, 3. Suppose we want to know how many connected components show up at time 2 and disappear by time 3. Well, we're going to go back to our rank function and look at the square going up and to the left. And what we're going to do is we're going to add 2, subtract 2, subtract 1, and add 1. That evaluates to 0, so we get a 0 in the persistence diagram. Indeed, no connected component appears at time 2 that is able to disappear at time step 3. But this persistence diagram, I won't prove it to y'all in this tutorial. It turns out is Möbius inversion. Indeed, the persistence diagram is the Möbius inversion of the rank function. And this observation is really helpful, namely, especially if we're interested in computing multiparameter persistence homology. With the observation that applying Möbius inversion gives us the persistence diagram, it gives us a natural way of extending persistence to the multiparameter setting. Namely, we can apply Möbius inversion to get persistence over poset. Again, I won't spend a ton of time talking to y'all about this, but I just want to give a brief overview of how you might use Möbius inversion to do so. I've created a similar filtration now on the screen, but this time now it's a 2-parameter filtration, or it's a filtration over that poset P I've shown earlier. And what we can do is we can compute something called the birth-death function on all intervals in this poset. Now, I won't go through what the birth-death function does, but again, it's going to capture the number of connected components that appear at or before your starting point in the interval that die at or before the ending point of your interval. And again, in order to get the persistence diagram, we are going to Möbius invert. And so just like with our 1-parameter case, Möbius inverting, again, think combinatorial derivative, that is going to help us track the changes in this birth-death function. So it'll describe precisely when these connected components appear and when they disappear. All right, so that is my very brief tutorial on Möbius inversion and where it shows up in persistence, how it helps us extend persistence to the multiparameter setting. Thank you so much for tuning in.